Satellites are like artificial moons, they orbit our Earth high above us. These incredible feats of engineering have revolutionized our world. They connect us, inform us, and help us explore. Satellites are crucial for communication. They beam television signals and internet data across continents. Weather forecasting relies on satellites. They provide early warnings of storms and other natural disasters. Navigation systems like GPS depend on satellites. They help us find our way on land, at sea, and in the air. Scientific research also benefits greatly from satellites. They observe our planet and the vast universe beyond. A satellite, despite its complexity, is essentially a system of interconnected parts. Each part plays a vital role in ensuring its successful operation in the harsh environment of space. Let's delve into the core components that breathe life into these technological marvels. First and foremost, we have the power system, the lifeblood of the satellite. Just like humans need energy, satellites need power to function. This power typically comes from solar panels, which convert sunlight into electricity. Batteries are also used to store energy for when the satellite is in Earth's shadow. Next comes the communication system, the satellite's voice. This system allows the satellite to send data back to Earth and receive commands from ground stations. Antennas act as the ears and mouth of the satellite, transmitting and receiving signals. No satellite can function without a command and control system, its brain. This system acts as the mission control center, processing data, executing commands, and keeping everything running smoothly. It's the conductor of the satellite orchestra, ensuring all systems work in harmony. Lastly, we have the propulsion system, the feet of the satellite. While not all satellites have this, those that do use it to adjust their orbit or avoid space debris. This system typically uses small thrusters that expel gas to make subtle movements. Imagine you're building a spacecraft in your backyard. Ambitious, right? One of the first things you need to figure out is how to power your creation. In space, there are no electrical outlets. The most common way to power a satellite is by harnessing the sun. Solar panels convert sunlight into electricity. But what happens when a satellite orbits into the Earth's shadow? That's where batteries come in. They act as backups, providing power when solar panels aren't exposed to sunlight. Building a satellite is one thing, but how do we stay connected with it once it's hurtling through space, thousands of miles above Earth? That's where the communication system comes in, acting as the invisible link between our planet and these orbiting explorers. Just like we use radio waves to listen to music and watch television, satellites use radio waves to communicate with us. Antennas, those metal appendages sticking out from the satellite's body, act as both ears and a mouth, receiving and transmitting signals. When a ground station on Earth sends a command to a satellite, it's transmitted as radio waves. The satellite's antenna picks up these signals and relays them to the onboard computer, which processes the command and initiates the appropriate action. Similarly, when a satellite needs to send data back to Earth, its computer transmits the information to the antenna, which then beams it down as radio waves. Ground stations receive these signals, allowing scientists and engineers to analyze the data and learn more about our planet and the universe. The communication system is the lifeline of a satellite, enabling us to send commands, receive valuable data, and stay connected with these technological marvels as they orbit our planet. Section 5. Finding your way. Navigation and control. Imagine you're driving a car. You need a steering wheel, an accelerator, and brakes to control your movement and reach your destination. Similarly, a satellite needs a system to navigate the vast expanse of space, maintain its orbit, and point its instruments at the right targets. This is where the Attitude Determination and Control System, or ADCS, comes into play. It acts as the satellite's brain for navigation and orientation. Using a combination of sensors, actuators, and algorithms, the ADCS allows the satellite to maintain a stable attitude, or orientation, in space. Sun sensors, for example, detect the direction of the sun, providing a reference point for the satellite. Reaction wheels, which are spinning devices, are used to rotate the satellite around its center of mass, like a spinning top, changing its orientation. Magnetic torquers interact with Earth's magnetic field, generating small forces to adjust the satellite's orientation. These are just a few examples of the ingenious tools used by the ADCS to keep a satellite on track. The ADCS is crucial for ensuring that a satellite can perform its intended mission. Whether it's pointing a telescope at a distant star or beaming communication signals back to Earth, precise navigation and control are essential for success in the challenging environment of space. Section 6. Shapes and sizes. Choosing the right design. When we think of satellites, we often picture sleek cylindrical objects with large solar panels. While this is a common design, satellites come in various shapes and sizes, each optimized for specific tasks and budgets. CubeSats, for example, are tiny satellites typically measuring 10 centimeters by 10 centimeters by 10 centimeters, about the size of a loaf of bread. These miniature spacecraft are relatively inexpensive to build and launch, making them ideal for educational institutions and small companies venturing into space. Spheres are another popular shape for satellites, especially those used for communication. The symmetrical design of a sphere ensures that signals are transmitted and received evenly in all directions. This is crucial for maintaining consistent communication coverage over a wide area. Cylindrical satellites, on the other hand, are often used for Earth observation missions. The long, tube-like shape allows for larger instruments and sensors to be accommodated, providing more detailed views of our planet. Choosing the right shape for a satellite is a delicate balancing act, taking into account factors like cost, functionality, and the intended application. The optimal design maximizes efficiency while staying within budget constraints. Section 7. Building your own satellite, a step-by-step guide. Building a satellite may seem like a daunting task reserved for rocket scientists and engineers. However, with the advent of readily available components and open-source resources, even amateur enthusiasts can embark on this incredible journey. The first step is to define your mission objectives. What do you want your satellite to achieve? Are you interested in Earth observation, communication experiments, or something else entirely? Once you have a clear goal in mind, you can start outlining the technical specifications of your satellite. Next, you'll need to gather the necessary components. This includes a chassis to house the electronics, a power system, solar panels and batteries, a communication system, antenna and transceiver, a control system, microcontroller and sensors, and any mission-specific instruments. Once you have all the parts, you can start assembling your satellite. This involves connecting the various components, writing software for the microcontroller, and ensuring that everything is properly integrated. Before launching your satellite into space, rigorous testing is crucial. This includes simulating the harsh conditions of space, such as extreme temperatures and vacuum, to ensure that your satellite can withstand the journey and operate as intended. Section 8. CubeSats, small satellites, big impact. In the realm of space exploration, size isn't everything. CubeSats, those tiny satellites that can fit in the palm of your hand, have revolutionized the way we think about space research and technology development. These miniature spacecraft, often built using off-the-shelf components, offer a cost-effective and accessible platform for a wide range of missions. From Earth observation to fundamental research, CubeSats are pushing the boundaries of what's possible in space exploration. One of the key advantages of CubeSats is their affordability. The reduced cost of development and launch makes them ideal for universities, research institutions, and even small companies looking to gain a foothold in the space industry. Moreover, CubeSats can be deployed in constellations, with multiple satellites working together to provide more comprehensive data coverage. This is particularly useful for applications like Earth observation, where a network of CubeSats can monitor large areas simultaneously. The rise of CubeSats has democratized access to space, empowering a new generation of scientists, engineers, and entrepreneurs to explore the final frontier. These tiny satellites are a testament to the fact that big dreams can come in small packages. Section 9. Conclusion. Reaching for the stars. As we've explored the intricacies of satellites, from their essential components to the step-by-step process of building one, it's clear that these technological marvels are within reach of anyone with curiosity and determination. The journey of building a satellite, whether it's a simple CubeSat or a complex orbiting observatory, is an exercise in problem-solving, innovation, and pushing the boundaries of human ingenuity. It's about turning dreams of exploring the cosmos into tangible realities. So if you've ever looked up at the night sky and felt a sense of wonder, remember that the stars are not out of reach. With passion, perseverance, and a thirst for knowledge, even the most ambitious space exploration goals can be achieved. As we continue to explore the cosmos, the possibilities are as limitless as the universe itself.